Hey YouTube, so today we're going to do problem number 10 from the section, from chapter 7, from the section on the natural response of an RL circuit. So this circuit has a 30 milliamp independent current source in parallel with a 1K resistor. At time 0, or before time 0, we have a closed switch connected in series with a 9 kilo ohm resistor, and that's connected to a parallel pair of 10 ohm resistor and some inductor of value L. So what we're looking for in part A is we're looking for the inductance that will give us 1/2 of the initial voltage across it. So it has some initial voltage. We're looking for an L that will give us 1/2 of that initial voltage after 1 millisecond. And in part B, we're looking for the percentage of stored energy that has been dissipated in the 10 ohm resistor when time is at 1 millisecond. So I actually found the actual joules. So I'm going to let you guys find the percentage because that's pretty easy. Okay. So let us get started. So I kind of went about this problem the long way, but it doesn't matter. It ended up working. It wasn't the most slickest way. So I'll tell you when I get to the point where I realize I could have done this a much easier way. So first let's look at the circuit at time before time 0. So before time 0, the switch is closed and we have 30 milliamps going like this. We have 1K here, the switch is closed, and then we have 9K here, and we have 10 ohms there, and then we have an inductor that's behaving like a short circuit. Well, since it's behaving like a short circuit, that means that it's shorted out that 10 ohm resistor. So we have this 30 milliamp going in here, and it's going to split by like that, and what we want is we want the initial current through the inductor. So so I0 then is going to be we're going to use current division. So current division says that the current through a particular branch is the same as the equivalent resistance of all the parallel connected branches divided by the one that you're interested in. So 1K in parallel with 9K is 900. Okay, so that's the equivalent resistance of all the parallel connected branches. And the one that we're interested in then is the 9K. So 900 divided by 9K times that 30 milliamp. So that's going to be 3 milliamps that's going through there. So I0 is 3 milliamps. Alright, so then the switch opens after time 0. So when the switch opens after time 0, we basically have this. We have this circuit like that. So we have this 3 milliamp traveling or going in a circle in there. And it has a certain voltage with it. And since these two are parallel connected, we know they'll have the same voltage drop. So then this V is going to be the 10 ohms times 3 milliamp. So that's going to give me 30 millivolts as the initial voltage drop. Now if you didn't see that, you could also use the equation, the general equation for voltage across the inductor, which is VL of T is equal to I0, the initial current, R e to the minus L over R, or R over L, excuse me, I think it's R over L. Yeah, it's R over L. So R over L T. So then you could just say it's going to have the most power at time 0, obviously, because it's not connected to any other power source, so it's going to have its maximum charge at times 0. So then you substitute a 0 in there, and then suddenly you have e raised to the 0 power, and anything raised to the 0 power is going to be 1. So then that goes away, and then you're left with I naught 0, which is 3 milliamps, excuse me, 3, so that's going to be 3 milliamps, and then R, the R in that is going to be the R seen by the by the inductor once it becomes an active element. So the only R that it's seeing is the 10. So the 9K is not connected to anything, so it doesn't see that. So then you would still end up with the same answer, which is 30 millivolts. So then I said, well, that's initial charge, so I'm looking for 1/2 of that. So I'm looking for, and then I wrote the general equation. So I said then the general equation of the inductor then is VL of T is equal to IR, which is going to be 30 millis, or 0.03. So that's going to be 0.03 times e to the minus L R, which is going to be 10 over L, and then times T. And then I said, okay, well, we're looking at 1 millisecond, so then I substituted 0.01. That's 1 millisecond. And then I said, and we're looking for 1/2 of the initial value. Well, the initial value was 30 millivolts, so I'm looking for 1/2, 15 millivolts. So 0.0115. So that's going to be 15 millivolts. And then I said, okay, so now it's just a logarithmic equation that you can solve for L. And then when I did this, I realized I did this the whole wrong way. So then I said, okay, let's divide by 0.03. Let's divide by 0.03 and realize that I could have just started with this and set the general equation for the voltage and just set it to 1/2. So e to the minus 10, what's minus 10 over 0.1? So then we got 10 divided by, times, so 10 times, times 0.1 e minus 3 will give me 0.01, so this is going to be negative 0.01, negative 0.01 t is equal to 1/2. So then you take the natural log of the entire equation, and that's going to give you, so I'm going to put the t here, so the t comes down, negative 0.01 is equal to natural log of 1/2, solve for t, so t is going to be natural log, oh, I lost my L somewhere, sorry you guys. So over L, and then that's not a t, so we put in, so it's negative 1 over L, so then we're solving for L, negative 0.01. Okay, so this is going to become over here, negative 0.01 over L is equal to natural log of 1/2. Okay, so now we can just solve for L. So L is going to be negative 0.01 over natural log of 1/2. So then we're going to go negative 0.01 divided by natural log 0.5, solve. Okay, negative 0.01 divided by the natural log of 0.5 So then the value, so for part one, the value that will give me 15 millivolts after 1 second is going to be 14.43 millihenries. So that's the answer for part A. And then for part B, we're finding the energy. This is just a straight application of the equation in the book. So part B is pretty easy. Just going to plug in. So we have energy is equal to 1/2 L I naught squared times 1 minus e to the 2t over tau. So then tau is L over R, right? And so that's going to be 1443 millihenries over 10. I naught is going to be 3 milliamps. L is going to be 1443 millihenries. Okay? And T is 1 millisecond. So do all that and you should come up with energy after 1 millisecond is going to be 4.898696 e to the minus 8 joule. Not e, I shouldn't, because times 10 to the minus 8, I should say. Times 10 to the minus 8 joules. So just plug in those numbers, that's what you'll get. And that is problem number 10. Please share the video and give the Facebook page a like if you got free help today. Thanks.